can be solved. So let me try to make it more simple. Let us consider a weaker problem. So now let me assume that B is an oracle that is always 0 or always 1. So on every input of length k, it produces that secret value z. Okay? And now again I assume that oracle AI agrees with B on 1 minus delta fraction of inputs of length k. So you may think about B as some exponentially long string of length 2 to the k that entirely consists of ones or of zeros. And we may think about AI as also as of exponentially long string. So can we now learn that secret value z can never possess only true AI? Well, the answer is certainly yes. Certainly yes. We just have to consider all answers of AI on inputs of length k and take the most popular answer, the majority answer. And if delta is less than 1/2, then that majority answer is necessarily that secret value z. Okay? And the remaining question
is the simplest possible error correction code.
Yeah, it's just repetition code. Right, you're absolutely correct. Actually, yeah. And the only question is, can we do it in polynomial time? Well, certainly it's impossible if we don't have randomness. Just assume this is oracle B. Oh, sorry, this is oracle AI. Okay, so somewhere its values are 1, somewhere its values are 0. And we want to compute the most popular answer. And we have only a time polynomial in k. Okay? So if we have only polynomial time and we don't have randomness, so we can simply look at polynomially many cells of that oracle. And certainly we cannot produce correct majority answer for all possible strings of length 2 to the k. Okay? So we cannot compute efficiently the majority function of exponentially many values in polynomial time. But what we can do is we can amplify the majority. Okay? So assume they have an oracle, and what we want to do, and assume it has 51% of ones and 49% of zeros. What we can do is we can create a new oracle, a new string that consists of 99%, that has 99% of ones and 1% and only 1% of zeros. So we amplify the majority. Okay? And still we want to compute every character of this string, of this new string, in polynomial time for some reasons. Okay, can we do this? Yes, we can using expanders. So consider an expander that has such that these characters of the original string form its left party, the characters, the positions of the new string form its right party. Now consider edges of that expander, well, and they give us the way to make queries to the original string. And a nice thing is that there are expanders with sufficiently strong properties that have exponentially many vertices and only a polynomial degree. Okay? So just to sum it up, we can amplify majority of exponentially long string in polynomial time. Okay? Any questions? So now let me turn back to the delay diagonalization and to apply this amplification that we have got. Firstly, let me replace those strings xk that we had with sets of strings. So yk is the set of all strings of length k. Now, I again consider a lot of yk, so I have yn plus 1, y2 to the n. And now I'm going to proceed in a fashion that is quite familiar to you. It's much like delayed diagonalization, but now I have to care about that AI may disagree with B on some small fraction of inputs. So This is why the definition of B becomes more complicated, but essentially still the same. So on all inputs of length 2 to the n, I define B in the way that it simulates AI on inputs of length n, on all inputs of length n, takes majority value and outputs the opposite. Okay?
So what you plan to do probably is, if I understand correctly, so you have to, as you did before with 1 bit, now you want to have this encoding, efficient encoding by very large fraction, and on each level you have some epsilon, you need to correct epsilon error, and then delta error, and then you compensate for this using this expander amplification. This is the main. And the expander amplification is made locally, so you need only polynomial time thing, and not so this is the plan.
Correct. So, as Sasha said, the plan is to transmit, in some sense, to transmit this 1-bit value that we can compute on this side to that side, right? And for this we use our error correction code, that is the simplest one, just repetition. And at every step we can get delta fraction of errors, but when we can recover from this delta fraction of errors. Okay.
So I can't understand so quickly. So okay. So we actually change the definition of B now. B still B NP.
It's just it's just a non-deterministic machine.
But we need to care that B now is defined